Alright, lesson 69 is simplifying complex expressions. Alright, but before we get into that, let's graph out some simple stuff here. Graph the point 3, 4, and you guys know we go over 3 and then up 4. So we put that 1, 2, 3, 1, 2, 3, 4. We put that on the graph there. We put our point in there, and then it says find the distance from the origin. So what we could do is we could draw in this triangle here then. Alright, because we would come across here 3, and then we would go up 4, and what would happen is we would have this right triangle here to be able to figure out that distance between them. Now you guys know you could use distance formula, but at the same point we could just do Pythagorean theorem, because we know that this side is 3, the bottom side is 3, and then we know the right side here is 4, which then we do Pythagorean theorem, we go 3 squared plus 4 squared, okay, equals what? So 9 plus 16 is 25, and then we would have to take the square root. So that final distance would equal a 5 here. Alright, now that's how we graphed our original ones. Okay, now we're going to deal with complex equations here. So let me get rid of this stuff here, and then go from there. Did not want to do that. Alright, so we'll get rid of these, get these off of the graph. Alright, and then we've got 2 minus 3i as the very first one that we need to do here. Alright, and how we do that, that's hard to do when we're dealing with a regular plane, so we've got to come up with a new complex plane. Alright, our x-axis is normally our x, but what it's going to be for this is going to be the real axis, and then the top, our y, normally our y, we're going to rename that and make that the imaginary axis. So what we've got here is we've got 2 minus 3i. So how we're going to do that is we're going to come over 2, and then, so we're going to come over 2, and then it says negative 3i, so we're going to go down 3i, and there is our point. Alright, so 2 minus 3i. For our next one, negative 6 plus i, we would go to the left 6, just like you normally would. So 1, 2, 3, 4, 5, 6, and then up 1i, so we'd have that point there. For 0.5i, we don't have anywhere to go on the right or left part. We would go up 0.5. And then for our last one at 0, that would mean we're going right or left 0, and up and down 0. So that would be that point right there. Alright, what we would need to do for this is we should be labeling out these points. So this would be 2 minus 3i. Alright, just like you normally would, you don't have to put it into an ordered pair because it's assumed that if we put those there, that's what it would end up being. Alright, but you should do that for each one of these 4 as you put them on there. So the next one, it says find the distance from the origin for the point 2 minus 3i. Well, what we could do is we could do the exact same thing as we did for this original one with 3 and 4. Alright, we could just draw these lines in here. Alright, so this first one would be going down 3. For our next one, we would be going to the right 2. Alright, so it sure looks again like we have some sort of triangle, and that's what would end up happening here. We want to find the distance from this point all the way down to this point. Well, once again, just like we did before, we know that this distance here, the distance is 2. We know the distance here on the graph is 3. So what we can do to find how long is the hypotenuse, we can still do Pythagorean theorem. So we can go 2 squared plus 3 squared, and then we take the square root of that. So what we get for an answer then is we would get the square root of, well, 2 squared is 4, plus 3 squared is 9, 4 plus 9 is 13. So our answer is the square root of 13 here for the distance between the origin and this complex point there. Okay, so it's still a Pythagorean theorem when you graph it out. All right, for this next one, when you find the absolute value of one of these complex numbers, absolute value, remember, is just simply finding the distance from the origin. So finding the distance from the origin, well, what we do here for this one was we did Pythagorean theorem. Well, we don't necessarily need to graph that out to find the absolute value of these numbers. We would square the first one, so we'd get a 25, plus squaring the 2 would be a 4. So what would we get for an answer is we would get square root of 29 for that first one. For the second one, we do the exact same thing. We go 25, or 5 squared is 25, plus 2 squared is 4, equals, again, the square root of 29. All right, and then for our last one, we've got 8i. Well, we don't have a real part like we did over here, so it'd just be a 0. So if you really wanted to, we could go 0 squared plus 8 squared is 64, and then take the square root of that. Well, square root of 64 is just an 8. All right, so we're just doing Pythagorean theorem for these when we're asked to find the absolute value of each one of these complex numbers. All right, when we come down here and it says to multiply these, all right, all we would do is we would multiply and kind of FOIL these out. So we would take 2i times negative 2, which would be negative 4i, minus 2i times 2i would be a 4i squared. And then what we learned was I squared is equal to negative 1. So if we put a negative 1 in here for this I squared, it'd be negative 4 times negative 1, which would be a positive 4 minus 4i. Now, in the directions, it says that we need to try and put it into this format, and we should. We should put the real number first and then the imaginary number second, and that's why I kind of reversed the order here. Even though this part here was second, I knew that we had to put the real number first, so that's why I put this positive 4 out front. For this next one, when we're multiplying two complex numbers, we just FOIL it out. 1 times negative 9 is negative 9. And then we've got 1 times negative 2i, so minus 2i. I times negative 9 would be negative 9i. And then we have I times negative 2i, so minus 2i squared. And then from there, we just combine like terms. So once again, we know this I squared equals negative 1. So this would turn into a positive 2. Negative 9 plus 2 would be a negative 7. So there's our real part. Negative 2i minus 9i would be a negative 11. So we've got negative 7 minus 11i. All right. Now remember, for this, we started talking, the I here doesn't change. So that is going to stay equal to I. As we said on the last problem, I squared would equal a negative 1. I cubed would be a negative I. And I to the fourth would equal a positive 1. So when we deal with these, we are looking at I to the 27th. We're going to take 4 divided by 27, and then we're trying to figure out how much we have left over. So 4 goes into 27 6 times, so that would go up on top of our division bar, and then 6 times 4 is 24. All right, and then we end up subtracting these to get a 3 down here on the bottom. And the 3 is the only thing that we truly care about, because what that means for this I to the 27th, that means it's going to be equal to I cubed, which would then be equal to negative I as we head over here on the side. For this 3I to the 333rd, all right, that's going to go into a ton of times. All right, we can still do this 4 divided by 333, and what would end up happening here is we would just be left with an I to the first power, so this would just be equal to 3I here. All right, and then down here on the bottom, we can do that 9 divided by 4. We would have 1 left over. So this would end up being a negative I. So even though we have numbers in front of these, like this 3 up here, we just leave that alone because we only care about simplifying the I to the whatever power. Down here with the negative, we just leave that there. We deal with the I to the 9th and simplify that down also. All right, last page. We've got 10 divided by 2 plus I square roots of 2. Alright, so how do we get rid of that? We're going to have to multiply by the conjugate. Alright, so we're going to multiply both top and bottom by 2 minus I square roots of 2, and I can't type in that square root sign. So you're just going to have to pretend that that's there. But we take top and bottom times that. So then, on the top, we would end up with just FOILing that out. Alright, so we would get 20 minus 10I times the square root of 2. And if we have to simplify that in a little bit, we will. On the bottom, we've got to FOIL all this out. We've got 2 times 2 is 4. And then we've got 2 times negative I squared root of 2, so that'd be minus 4I squared root of 2. For this next one, I squared root of 2 times 2, that would be plus 2I squared root of 2. And then minus, we would have an I squared times 4, or no, we'd have a 2I, no, times the square root of 4 here, which square root of 4 would end up being a 2. So we'd be able to simplify this down quite a bit. Alright, and the bottom we definitely have to simplify out. We've got this I squared here, which would be a negative 1. Negative 2 times negative 1 would be a positive 2. So 4 times 2, or 4 plus 2 is 6. And then we can simplify these down. So we've got negative 4I squared root of 2 plus 2I squared root of 2. We would end up with a negative 2I times the square root of 2 here. On the top, we would still have this 20 minus 10I square root of 2. Alright, and then what should happen here is we still have an I down here. Alright, so we got to go back and actually figure out what happened here. On the top, 2 times 2 is 4. 2 times I squared root of 2 is not 4I squared root of 2. It is 2I squared root of 2. And then what should happen is these two cancel out, and that is what does happen here. Alright, so these would end up going away. We would just have a 6 on the bottom. Alright, and then we can simplify these down because we have this 20 minus 10I squared root of 2 over 6. We could divide the top, everything on the top by 2. So this would be a 10 minus 5I squared root of 2 over 3. And that would then be simplified. For this second one, we're going to skip this one for now, but you do the exact same steps with that. You got to get the I out of there, so you'd have to multiply top and bottom by I, and then simplify those down from there. and that is